So just in general, energy can be divided into two different types. It can be divided into mechanical energy and non-mechanical energy. Our mechanical energy is kinetic energy and potential energy. We can determine the thermal energy if we know how much kinetic and potential energy was lost from a system. We can figure out how much of that energy was possibly converted to heat through friction. But we're going to focus mainly on the mechanical side. So kinetic energy is basically the energy of motion. Potential energy is based on an object's position. So where it is in location to other objects, where it is in a field, or different types of things. So we're going to deal a lot with mechanical energy. So kinetic energy is due to an object's motion. So objects that are in motion have kinetic energy. Now we have two basic types of motion that we're going to take a look at. We have translational motion. So this is our linear motion, which we've been looking at. We also have rotational kinetic energy. Rotational kinetic energy we will talk about when we get to our units on rotation. So for what we're talking about now, we're talking about translational kinetic energy. So translational kinetic energy is an equation 1/2 mv squared, where K is our kinetic energy. Kinetic energy, and all energy is measured in units of joules. M is our mass of the object in kilograms. V is our velocity. We just need the magnitude of the velocity because of the squared, in meters per second. And so that is the magnitude of the net velocity. So if it was a 2D motion problem, that would be the overall velocity, not just the velocity in the X or Y dimension. So basically what this tells us is that our kinetic energy is proportional to mass, and our kinetic energy is proportional to our velocity squared. So if I double my mass, I'm going to get double the kinetic energy, but if I double my speed, my velocity, I'm going to get 4 times the kinetic energy. So changes in kinetic energy are going to be largest when you have very large changes in speed. So another thing this tells us is because mass is a scalar value and is always a positive scalar value, and velocity is squared, this tells us that our kinetic energy is always positive. It can never be negative. You can never have negative kinetic energy. We are specifically going to look at gravitational potential energy today. And gravitational potential energy is actually very, very complicated. There's ways to simplify it down, but remember that this gravitational potential energy is due to an interaction between objects with mass separated by a distance. So basically any object that has mass is exerting a gravitational field, and that field can be felt kind of everywhere around it. Actually, you'd have to get infinitely far away from an object in order to not experience a gravitational field. But there's no gravitational potential energy until I put a second object into that field. So basically the gravitational potential energy is due to an interaction between objects with mass. Now, we generally look at objects with very different masses, so like the Earth and a ball type situation. So we often look at the fact that, hey, this is the larger mass, it's the one exerting the gravitational field, and then this is the smaller object, it's the one that's going to be accelerated by that gravitational field. But it requires both objects. So I have to define my system as containing both objects in order to have gravitational potential energy. I can have a gravitational field by just looking at this object. This object is exerting a gravitational field, which would have a tendency to attract objects to it. But it on its own cannot have gravitational potential energy. A single isolated object cannot have gravitational potential energy. In order to have gravitational potential energy, you have to have a second object in that field. The other thing that we have to consider is we cannot measure the absolute gravitational potential energy an object has. There's no way to determine. All we can do is we can only determine the changes in potential energy. So we can only determine the changes in gravitational potential energy. So, for example, if the mass is here at this position, so it's located at this particular position, position 1 here, and then it were to move closer, then it would have a different amount of potential energy. And so I can't know exactly how much potential energy I have here or here, but it is possible to determine it based on the change in position. So I can analyze the change in position and determine what the change in gravitational potential energy would be there. Now, this is still a very complicated situation. And that's because the gravitational force itself is not constant as you move objects closer and further. So for what we're going to do here is we're going to analyze situations that are close to Earth's surface. So we've talked about being close to Earth's surface before. So if we are close to Earth's surface, or the surface of any gravitational mass, then we are approximating the acceleration due to gravity as constant. So our acceleration due to gravity is approximately constant. So when we're looking at close to the surface of an object. So I can consider my Earth, since I'm close to it, to essentially be horizontal here. So this is my Earth. And then I also have like my other objects. So maybe the ball. So this is my ball. So I'm looking at the Earth ball system. On the AP Physics 1 formula sheet, if you were to look up gravitational potential energy, you would find that UG is equal to mg delta y. So they use capital U for potential energy. The subscript G is for gravitational potential energy. And what they're assuming here is that there is some sort of gravitational potential energy here at position 1. There's some sort of gravitational potential energy at position 2. And technically, we can't actually know the potential energy at position 1 and 2. We can only know the difference. But here's what we're going to do to simplify this down. We're going to assume that we always set the lowest point in the motion to have no gravitational potential energy, whatever it is. If it's going down a hill, if it's a pendulum swinging in a circle, whatever the lowest position, we just assume that that height is 0. So we're going to assume that h equals 0 at lowest position. And because that's the lowest we go, we don't have any potential to fall once we get to that lowest position. So what we can do is we can just define our gravitational potential energy to be 0 at that lowest position where we set the height equal to 0. So what that does to this equation is that now sets, we can define here at the bottom h equals 0. So UG here at the bottom is just going to be 0. And then I'm going to define this height here to be h that I am at. So at this point, we're going to have a UG equal to mgh, and that's the amount of potential we have. So what we've essentially done is we've done like UG2 minus UG1 for delta UG is equal to mg times our delta y. But technically, if you go from UG1 to UG2, this delta y would come out negative, and it would equal negative h. So if you actually did delta y, that would be a negative h because you're going kind of in the negative direction. So this is going to be mg negative h. And we're going to let our UG equal 0 at the bottom, so UG2 is going to be 0. So you get negative UG1 equals negative mgh. So we're just going to call that a positive, and our UG at position 1 is just going to be mgh. So basically we can simplify this whole down equation to assuming that I set the lowest point of the motion to a height equals 0, I can find the potential energy at any point above that as long as I stay close to Earth's surface as having a gravitational potential energy equal to mgh, where m is the mass in kilograms, g is our 9.8 meters per second squared, magnitude of our acceleration due to gravity, and h is going to be the height in meters. Now this g, I could take this to the moon, which has 1/6 the acceleration due to gravity, and so I would have 1/6 of 9.8 meters per second if I did this on the moon instead. So that kind of gives us kind of like a basis to work with potential energy. So why do I know that my ball is at higher potential here than lower potential here? Well, I would know that by understanding our definitions of kind of potential energy, and basically all objects tend to freely move from high potential to low potential. So objects have a tendency to freely move from high potential to low potential. So if this ball starts off with a speed of 0, and then it hits the ground with some sort of maximum speed, I have gained kinetic energy. So as I fall, I gain kinetic energy. Well, in order to have gained kinetic energy, that energy had to come from somewhere. And so what happens is I had to have lost potential energy. So that's how I know that my ball was at higher potentials, because I gained kinetic. That meant I had to lose potential.